802.1p/q virtual LANs and cost tagging. So remember in the previous video we discussed the evolution from 2008 where it allows to add tagging and priority and multiple VLANs in that Ethernet or envelope frame. Now we will discuss some of that now with regards to the application in real world. With the growing use of switch Ethernet, it has become possible to interconnect every computer at a site on the same Ethernet LAN. The advantage of doing this is that any host can directly communicate with other hosts using IP and other network layer protocols and requiring little or no administrator configuration. So because of this switch Ethernet that support multiple Ethernet or even Wi-Fi, it becomes possible to connect every computer at a site on the same Ethernet LAN. So as long as you have same Ethernet LAN, you can connect them. You can even separate them logically, which we're gonna discuss later. The advantage of doing so is that any host can directly communicate with any other host using IP and other network layer protocols and requiring little or no administrator configuration. So if you just have the IP address, you will be able to communicate with the other host without further configuration. In addition, broadcast and multicast traffic, see Chapter 9, is distributed to all hosts that may wish to receive it without having to set up special multicast routing protocols. So if you have a source as a broadcast or multicast traffic that is distributed in that same Ethernet or LAN that may wish to receive it without having to set up a multicast routing protocol, which we discussed in the previous video. Well, these represent some of these advantages of placing many stations on the same Ethernet. Having broadcast traffic to go to every computer can create undesirable amount of network traffic when many hosts use broadcast, and there may be some security reasons to disallow complete any-to-any station communication. But there's an issue. It may not be ideal to do that because for security reasons and for performance as well. To address some of these problems with running large multi-use switch networks, IEEE extended the 802 LAN standards with a capability called virtual LAN in a standard known as 802.1q or 802.1q 2005. Compliant Ethernet switches isolate traffic among hosts to common VLANs. So for all of the Ethernet cable that is compliant with this new standard, they are able to isolate traffic among hosts to common VLANs. So they're able to separate it using VLAN, which we're gonna discuss. Note that because of this isolation, two hosts attached to the same switch but operating on different VLANs require a router between them for traffic to flow. So what does that mean? We're gonna explain here. So basically, if you have one switch that has this Ethernet supported cable that support the separation via VLAN, you need a router if they are in different VLAN to send packet to them. So imagine this in your Ethernet router. For me, I'm using Converge. So you have two network interface there. You have the Ethernet sorry, you have 4 ports. So port 1, where your laptop A is connected via Wi-Fi signal, and then port 2 is the Wi-Fi router. Port 3 is the laptop B, where it is connected via Ethernet, and port 4 is, for example, your printer. So for VLAN 20, anything or any packet sent from VLAN 20 to VLAN 10 needs a separate router to connect via network layer, instead of just staying on the link layer, which is the Ethernet cable. So you need to go up to the link layer, or you need to know the network protocol such as IP address to be able to connect with them. So here VLAN 10 traffic is isolated from VLAN 20 traffic. Laptop A cannot talk to laptop B directly because they have different LANs. They need router layer 3 to interconnect VLAN to VLAN 20. This is layer 2 isolation. Each VLAN acts like its own little Ethernet LAN. So because this Ethernet cable support this VLAN separation, though they are running in the same cable physically, they're actually separated logically by this VLAN. So they cannot really connect to them in link layer. So you need an IEEE activation or IEEE Ethernet VLAN capable router for that. Now connect that to your converged ONU router. So your ONU router internally looks like a small layer 2 switch that support multiple VLANs. So it looks like this. You have a router, VLAN 10 equals to home LAN, VLAN 100 internet uplink. So Wi-Fi Ethernet ports one side to converge, and then it connects to converged network. So this VLAN 100, it's actually a connection of your converge to the internet. So here's what's happening. VLAN 10 is your local VLAN. It is inside your house. That's where the laptop A and router port is connected via the link layer, and your phones as well could be there. 100 is an internet uplink. It's connected outward. It is connected to the internet whenever you're sending it via NAT and DHCP. You're sending it via this VLAN. Though you only have one cable outside connecting, you're gonna see a cable. Those the packets going out of there is actually different. Could be different VLAN, because the reason Converge do that is because to separate the packets or frame for TV management traffic and then the internet, to separate those three. So though you're seeing one fiber network or fiber cable, it is actually separated by VLAN. So these VLANs are completely isolated at layer 2 traffic from VLAN 10 cannot flow into VLAN 100 directly. They need to go up to the higher level, such as layer 3, to be able to connect here. So who connects them? The router function inside the ONU layer 3 device. So the thankfully your Wi-Fi has a router inside it that allows them to connect those two switch. It actually accept the traffic from your VLAN 10 host and then send it to the internet via its own router. So your ONU has two virtual interfaces. Interface F0.10 for VLAN 10, IP network 192.168.1.1/24, LAN ETH 0.100 VLAN 100, IP network, public, or PPPoE IP1. So these are the IP address this VLAN connected to. So you have two interfaces in your router to be able to do that. When your laptop 192.168.1.10 sends a packet to the internet, it goes into VLAN 10 LAN. The ONU router routes it layer 3 to VLAN 100. So it's kind of like link layer 3 to link layer 2 again, because VLAN 100 is in link layer 2. VLAN 100 sends it to converged access switch. The switch forwards it to the ISP core router, and then it routes it to the internet. The router inside your ONU is the layer 3 bridge that connects two isolated VLANs. So that's what this chapter, that's what VLAN's all about. It's about isolating a network to be able to send separating them in a link layer point of view in TCP/IP. So connect another thing is that the fiber, if you're most of the internet are using fiber now, if you're using fiber, those happen in like lightning fast. That's why it's you're able to connect to the internet so fast. Connect it to textbook line directly. Textbook concept. Switches isolate host into VLANs. Converge real-world equivalent. The ONU separates LAN N1 into VLAN 10 and VLAN 100. So it actually separates that into that actual number, VLAN 10 and 100. Hosts in different VLANs can talk directly. Your Wi-Fi laptop LAN VLAN 10 can't directly reach the ISP. Hosts in different VLANs can talk directly. Your Wi-Fi laptop LAN VLAN 10 can't directly reach ISP VLAN 100 without routing or without layer 3. So they're not connected via layer 2. A router is needed between VLANs. The routing or NAT function in your ONU, or the NAT table in your ONU, allows that to know which device send and then connect it using the unicast address provided to it to the converged access switch. Compliant Ethernet switches prevent leakage. VLAN tagging 802.1q ensures your local LAN traffic doesn't mix with converged uplink data. So if that Ethernet is IEEE compliant, it will allow that separation, because again it's one fiber or Ethernet, but it's actually separating the packets logically. Now VLAN tagging, so the way it does that is we're gonna discuss later, is it adds some VLAN ID header and a priority. So that actually how you configure it through your router, the priority of packets of devices on your network, and that's actually how you prioritize when you connect the laptop or computer directly to your router. So compliant Ethernet switches prevent leakage. VLAN tagging 802.1q ensures your local LAN traffic doesn't mix with converged uplink data. So that's what make it separate that logically, even though they are in the same fiber. So that's the Ethernet frame we discussed. So these are the application in real world of that VLAN ID separation and the queue tag or the priority queue. So there's a diagram. The LAN VLAN 10 is in interface .10 192.168.1.1 IP address. Layer 3 routing to be able to connect to this VLAN 100, which is interface ETH0.100 public IP / PPOE in your router. So that's the converged fiber network, and that VLAN 100 802.1q supported is connected to converged access switch. So even though ONU router is one box, inside it there are two VLANs, isolated layer 2 domains joined by layer 3 router. So here layer 1 physical fibers carries light signals between ONU to ISP. So that's what it connects. That's why it's also fast, because it's it carries light signals. Layer 2 data link VLAN 10 and VLAN 100 isolate Ethernet traffic. So that type of Ethernet that links them isolates that traffic logically, not physically. Layer 3 network router moves IP packets between VLANs, NATs from private to public IP. So that's the layer 3. Layer 47 TCP or IP session and apps, HTTP, HTTPS, DNS, etc. use that routed connection. Combination of switch or router devices have been created to address this need, and ultimately the performance of routers has been improved to match the performance of VLAN switching. Now the performance of this combination has been improved to match that previously separated switch. Thus, the appeal of VLANs has diminished somewhat in favor of modern high-performance routers. Nonetheless, they are still used, remain popular in some environments, and are important to understand. Several methods are used to specify the station to VLAN mapping. Several methods are used to specify the station to VLAN mapping. So how do we assign that? Assigning VLANs by port is a simple and a common method, whereby the switch port, so a common method which is a VLAN, assigning this VLAN by port in this combination of router and switch is a simple and common method, whereby the switch port to which station is attached is assigned particular VLANs. So any station so attached becomes a member of the associated VLAN. Again, whereby the switch port to which the station is attached is assigned a particular VLAN. So the station is connected to that switch port and it is assigned a particular VLAN. So any station so attached becomes a member of the associated VLAN. So any station attached to that port will become a member of that VLAN. Other options include MAC address based VLANs that use tables within Ethernet switches. So it uses tables to track the MAC address, to map a station's MAC address to a corresponding VLAN. So it maps the station MAC address instead of the station directly connected to port to the VLAN. So this become difficult to manage if station changes their MAC address, which they do sometimes thanks to the behavior of some users. So some users, like change computers, IP address can also be used as a basis for assigning VLAN. So IP address can be used as well. So it can be port, MAC address, or IP address. When stations in different VLANs are attached to the same switch, when stations in different VLANs are attached to the same switch, the switch ensures that the traffic does not leak from one VLAN to another. So when you have a lot of stations with different VLANs, this switch ensures that the traffic does not collide with other, irrespective of types of Ethernet interfaces being used by the stations. So that Ethernet interfaces could be a Wi-Fi interface as well. So irrespective of that, the way they connect to router, they make sure that it is logically separated. When multiple VLANs must span multiple switches, which what we call trunking. So when you have multiple VLANs in different switches, instead of just one switch coordinating all of the VLANs, it becomes necessary to label Ethernet frames with the VLAN to which they belong before they are sent to another switch. So if that's the case, if you have a trunking, you need to add a VLAN ID in your frame and encapsulate that. The one we discussed. Support for this capability uses a tag called the VLAN tag or header, which hold 12 bits of VLAN identifier. So 12 bits, that's 1.5 bytes something. So it has almost 2 bytes of VLAN identifier, providing for 4096 VLANs. Although VLAN 0 and VLAN 4096 are reserved. It also contains 3 bits of priority for supporting QoS. So 12 plus 3, so that those two are almost 2 bytes to be able to send to another switch to identify where it came from, defined in the 802.1p standard as indicated in the previous videos. In many cases, the administrator must configure the ports of the switch to be used to send 802.1p/q frames by enabling trunking on the appropriate ports. So in many cases, an administrator needs to configure the switch in that specialized port that will allow that trunking, or by sending it to different switches if they have different VLANs in different switches, by enabling trunking on the appropriate ports. To make this job somewhat easier, some switches support a native VLAN option in trunk ports. So again, to make this job somewhat easier, some switches support a native VLAN option on trunk ports. So this native VLAN is a native VLAN or a native LAN, a VLAN rather, that will be the fallback in case that the packets did not send inside the VLAN, or I mean if the VLAN if the frame doesn't have a VLAN header. So some switches support this other than configuring it in the forms. They have the trunk ports, meaning that untagged frames are by default associated with the native VLAN, so as not to lose frames, because if you, usually if you don't have a VLAN ID on your frame, it is not configured like that, all the frames will be lost. So in this case, it will go to the VLAN, native VLAN. Trunking ports are used to interconnect VLAN-capable switches. Trunking ports, or specialized ports on your switch, are used to interconnect VLAN-capable switches. Again, the switches needs to be capable or follow the standard of IEEE. So 802.1p/q, etc., and the Ethernet cable that connects them. And other ports are typically used to attach stations. So trunking ports are used to interconnect VLAN capable switches, and other ports are typically used to attach stations. So the other ports on that switch are typically used to attach stations into it. Some switches also support proprietary methods for VLAN tracking. So aside from enabling other ports and native VLAN and connecting different VLANs, some switches also, in addition for that, supports proprietary methods for VLAN trunking. Like the Cisco InterSwitch Link, or ISL protocol. So these proprietary methods allows for easier trunking if you're connecting different switches, such as Cisco InterSwitch Link, kind of like specialized hardware to support this kind of connection if this is more prevalent in your network. So manual banding link aggregation, we will discuss this in the next topic, which is the link aggregation, formerly 802.3 AD of IEEE. So we will gonna get a glimpse, or basically once we understand this, it will be easier to understand that topic later. So manual banding link aggregation, what it is. Manual banding, also known as static link aggregation, means you combine multiple physical Ethernet interfaces, like say ETH0 plus ETH1 into one logical interface, which is band 0. This increases bandwidth, multiple links used in parallel, redundancy. If one link fails, traffic keeps flowing. However, since you're manually banding, no LACP negotiation, you must configure both ends identically, because there's no protocol telling each side what to expect. So later we will discuss a LACP which does this combination. Essentially, you're connecting physical Ethernet interfaces in one logical interface. So it's kind of like doing a VLAN, but the purpose of this is like to increase reliability and to maximize speed. So some protocol supports this manual or configuration entirely without having to set this up, because later we will set this up in Linux OS. Both sides must match means every parameter related to the aggregated link must be manually matched on both devices, your host server and the switch it connects to. So to be able to do this, both every parameter on related to the aggregated link or that interface must match. So remember the Ethernet frame or the encapsulated frame format, it must match. Banding mode, example on host. Mode equals balance dash RR or mode equals 802.3 AD. Example on switch. Switch must have the same mode, manual or LACP. So to be able to connect this to Ethernet, the switch must be the same. So how do you connect to different Ethernet link? You need a switch, right? So this switch must have the same mode, the manual or LACP. Why it must match? Mismatch mode can cause packet loss or looping. So since let's say you have more encapsulated frame size than the other Ethernet interface, you're gonna have a packet loss. VLAN tagging. Example on host VLAN 10, ETH 0.10 or band 0.10. Switch port, example on switch, switch port must belong to VLAN 10. So to be able to tag that switch port must be belong to VLAN 10. Ensure traffic is routed correctly. So the VLAN tagging must match to ensure that the traffic is routed to the right VLAN. Cost priority 802.1p priority bits like 0 to 7. Switch cost policy for same class. So that's the example on switch. Why it must match? Ensures consistent traffic treatment. MTU frame size. This is the size. So 1500 or jumbo 9000 bytes. Same MTU configured and switch port. So the switch must have the same configuration for that, because again, switch is what divides that or encapsulate the frame. Why it must match? Mismatch causes draft frames. Trunking. So additional is trunking. Band carries multiple VLANs. So for example, you're trying to band different switches. Since those different switches could have different VLANs among different switches, it must support trunking as well. So example in switch port group must be trunk ports. So as one of the switch port group must be a trunk ports to connect different switch. Why it must match? Untag or tag frames must align, because for example, if one has the untag frame, there's like an a frame that is not encapsulated, it will go to the native VLAN. If one side expect untag frames and other expect tag 802.1q, communication will fail. So that's the reason why you need that trunking to support. So how it connects to 802.1p/q VLAN and cause tagging? When you trunk VLAN across your banded link, you're essentially doing this. Band 0 logical interface carries VLAN tag frames, switch trunk ports. So this band 0 is the logical interface. That's what will carry the VLAN tag frames, what switch encapsulate to the switch trunk port, and vice versa. And then router, TCP, etc. Each Ethernet frame can carry a VLAN ID 802.1q, tells which virtual LAN it belongs to. A priority field 802.1p, define cost level. If you don't tag correctly, the switch won't know which VLAN the traffic belongs to. So if you don't tag it, the switch won't be able to encapsulate it with the proper VLAN ID and send it to the right VLAN. And if you use cost, the switch must interpret your 802.1p bits the same way your host does. So that's the reason why it must match as well, because aside from the switch encapsulating it with the priority, your host must support it already. That's why they must be p/q IEEE supported standard. So example configuration on Linux. Mod probe banding. So these are the manual library that you need to import to be able to configure your switch to support this banding or link aggregation in different interface. IP link add band 0 type band mode equal 802.3 AD. Next line, IP link set ETH0 master band 0. Next line, IP link set ETH1 master band 0. Next line, IP link set band 0 up. So the master is band 0. You're putting ETH01 and ETH1 into the band 0 master, and then you activate that using this line, IP link set band up. Then you add VLAN trunk on the banded interfaces. This is how you add the VLAN or configure that as a VLAN trunk on these banded interfaces. So again, we need to configure that, for the switch to support the connection of different VLANs in different switches. On the switch interface range, gig 1/0/1-2 channel dash group 1 mode on static banding. Again, on the switch, this is what you will execute. Interface range in Linux, interface dash range gigi/1/1/0/1-2. Next line, channel dash group 1 mode on 2 static banding. Next line, switch port mode trunk. Next line, switch port trunk allowed VLAN 10,20. Next line, switch port trunk native VLAN 10. Notice how both sides know they're part of the same trunk group because those trunk allow multiple switches in different VLANs. VLAN 10 and 20 are consistent. MTU and frame types match. So notice how the frame size match there. And VLAN and 20 are consistent. How this relates to envelope frames we discussed in the previous video. When you add VLAN or COS tags, the Ethernet frames get slightly larger, extra 4 bytes from 802.1Q tag. That's why envelope frames up to 2000 bytes were introduced to accommodate tag frames and possibly other metadata. So if your banded trunk uses VLANs and COS tags, it's actually sending envelope frames. So if your banded trunk uses VLANs and COS tags, so if those different VLANs and different switches are banded, meaning they are configured to be high reliant and also to be able to connect different switches, and using a switch supported trunk ports with VLANs and COS tags in its brain, it's actually sending envelope frames, which we discussed in the previous video. Now, summary: manual banding equals to static link aggregation, no LACP negotiation. Both sides must match equals same banding mode. So they must be in the same banding mode. They must have the same VLANs, or they must be supported or connected via trunk. They must have the same MTU or size, maximum size. They must have the same tagging and trunking. 802.1 P/Q equals the standard for tagging VLANs. So these are the standard provided by IEEE2 for tagging VLANs. 802.1Q and COS priorities for 802.1P. Envelope frames, extended frame format that allows extra tag fields. So these are the concepts that we discussed in the previous video. In a banded plus VLAN trunk, all links acts as one. Carrying tag Ethernet frames 802.1 P/Q between devices. So in that network, all links acts as one. So on Linux, the host, this is how we configure it. Modprov banding, meaning loads the banding kernel module. So it drop into the kernel and module, which already in the Linux, which lets Linux create a logical interface band 0, combining multiple physical NICs, ETH0, ETH1, etc. So this banding kernel module or library, let Linux create logical interface like band 0 combining multiple NICs. So this ETH0, ETH1 we are keep discussing, those interfaces actually a network interface or NICs used to connect to devices or host or switch, so as long as they have NIC, where it fits in TCP or IP model. Another thing with this is that with kernel module, usually for Linux operating system, they are configured to be downloaded for just a default, not this advanced configuration. So if you want to import that, usually this being downloaded from the cloud. You need actually an internet to download this kernel module. So where it fits in TCP or IP model, this operates at layer 2, the data link layer, same as Ethernet. So this banding kernel module operates at the data link layer. The OS provide this, connect these interfaces, the NICs. It could be in physical layer as well because it has this MAC address or Ethernet interface, but it's primarily they're connecting that via layer 2 logically, again just like in the Wi-Fi earlier, in Converge, though they're in the same cable. Relation to envelope frames, each physical NIC will carry Ethernet frames, possibly tagged with VLAN and COS bits. So how it is related to envelope frames. Each physical NIC will carry Ethernet frames, possible tagged with VLAN and COS bits. So that's happening in the switch, right? Whenever it's trying to send from one station to another. So that will come from NIC, from physical, and it will be converted by the link layer, which is the switch, and then to the and then to the IP and the TCP or app of the next station. Now banding doesn't change the frame format itself. It just treats multiple NICs as one pipe that send those envelope frames. So banding kind of like just ensure that it is fast and reliable. So that's what we mean by mod probe banding. That's the module. IP link and band 0 type band mode equals 802.3 AD. So this created a banded interface band 0 using IEEE 802.3 AD. So that's link aggregation control protocol. So this is where the LACP comes from. This tells Linux that band 0 is made up of multiple Ethernet links working together as a single logical channel. So it's gonna like connect them logically as well, but using this instead of the manual configuration, the LACP. TCP or IP model. So basically this importing the LACP, and these are importing the mod probe that allows for manual configuration for us to provide a hybrid approach that allows us to automatically configure some interfaces and provides an automatic configuration for other interfaces. Now IP link add band 0 type band mode 802.3 AD. So that creates again banded interface. So where it is in TCP or IP model, still layer 2 Ethernet. This defines how frames are transmitted over physical links. So this layer 2 or this line of code basically defines logically how it would be transmitted using that one cable or that physical link. Envelope connection. So when traffic leaves band 0, it still gets wraps inside an Ethernet frame, which can include 802.1q or 802.1p tags. So if your upper layers like IP send a packet, band 0 will encapsulate it in an envelope frame for Ethernet transmission. So it's still in Ethernet, kind of like in these are in the the link layer. The first one, the mod probe, because it directly came from OS. But here is in the Ethernet. It defines the Ethernet, how it is connected to the upper layer, like IP. So this will encapsulate, for example, an laptop A send a packet to laptop B on another switch. This will encapsulate, this Ethernet will encapsulate it. This still in layer 2. It's still using envelope frame. For example, your frame that was sent from an IP has a priority, or if it's not have a VLAN ID, it will go to native VLAN. Now IP link set ETH0 master band 0, and then next line IP link set ETH1 master band 0. So these attach the physical interfaces ETH0 and ETH1 as members or slaves of the band. So this is how you band it manually using the mod bonding, what do you call this, mod probe bonding we imported. So it attached the physical interfaces ETH0 and ETH1 as members or slaves of the band. Now all traffic to or from band 0 is distributed across these two interfaces. So all the traffic that will be sent from other switch to this band 0 will be distributed across this. So let's say you send to band 0, it will be sent, all the interfaces or devices or hosts connected to it will receive it. So in TCP or IP model, this is the physical link aggregation portion. It's still layer 2 but touching layer 1 physical, since it's dealing with real NICs. So it has a 2-layer because it separates that, and since it's directly connecting to 2 NICs, it has some physical layers. So these are more one of the complicated part of this, because you have this 2-layer in this 2 lines of code. Now envelope connection, each physical port can carry tag Ethernet frames. So this each port or each interface can carry tag Ethernet frames. The envelope frame is replicated or load balanced across multiple wires transparently. So it is replicated. If you just send it to one band and then there's a 2 interface, it will be replicated. The receiving switch resembles them logically as one channel. So IP link set band 0 up. So the receiving switch, let's say that whenever that switch, that interface or NIC are connected, that receiving switch will duplicate that and reassembles them logically as one channel to be able to send it to the receiving host. Now IP link set band 0 up, so meaning it activates the banded interface so it can pass traffic. So this will like the activation part. So after we set it up, we activate it so it can now pass the traffic. So like basically we're doing this in software to be able to support that via hardware. TCP or IP model, it enables communication at layer 2, which allows upper layers IP TCP to function. Envelope connection, so once band 0 is up, Linux can now start sending Ethernet frames or envelope frames that carry TCP or IP data, layer 3 to 4 payload. So now all hosts that has the TCP or IP payload on their computer will be able to send packets to a different station from a different building, as long as these are set up. So optional VLAN slash cos tag inside the Ethernet envelope. So if you're trying to send to a specific VLAN, you can add a frame. But if it's not sending to a specific VLAN, it will be sent to a native VLAN. Now vconfig add band 010 and vconfig add band 020. What this means, it creates a virtual sub-interfaces for VLAN 10 and VLAN 20 on top of the banded link. So on top of the banded link, there's a virtual sub-interfaces created here. So band.10 and band.20 act like separate virtual network cards that automatically tag every outgoing frame with VLAN IDs 10 and 20 using 802.1q header. So because you separate this, like you banded two ports, this interface will allow or will convert every frame being sent to all the parts of this band ports with using the 802.q header with the VLAN ID and 20. So TCP or IP model VLAN tagging is still equals to layer 2 Ethernet, but this separation allows layer 3 IP traffic to be logically grouped per VLAN like separate subnets. So this configuration allows the layer 3, so from the packet side, to be or IP packet to be logically grouped per VLAN like a separate subnet. Envelope connection. Now your Ethernet frames get a VLAN tag field like a 4 bytes added. So this is where you have the VLAN tag field. So this transform them into envelope frames because they're carrying extra tags like VLAN ID and cost priority beyond the normal Ethernet frame. So this is how you send a packet from one separate building station to another using a VLAN ID. So band 10 and then that is actually how you use banding. So when you're sending like a packet, it is separated kind of like in layer 3 by these virtual interfaces using band 10 and band 20, and all of the physical interfaces or port will receive that, and it will be configured and balanced based on the band configuration, or if there's an LCAP configuration. So here instead of dest MAC or source MAC, type payload CRC. Now you get dest MAC, SRC MAC, 802.1q tag VLAN plus 802.1p priority, type payload CRC. This is what the 802.3 2008 section meant by frames containing 802.1p/q tags are envelope. So ifconfig band 0.10 up, so and then next line ifconfig band 0.20 up. This Linux configuration, meaning it activates the VLAN tag interface so they can send or receive packets. So now that virtual interface will be activated so that they can set packet from an IP or layer 3, and it can be configured using band, and they can be controlled in layer 3 for reliability and bandwidth. So band, for example, we can create band.10 to 192.168.10.5 IP address, and band.20 to 192.168.20.5. So this is how we include the IP layer 3, because now we can now assign an IP address to that band, so that anything IP packet sending to this IP will go to that band. So and then that band will be handled depending on LCAP and band configuration within it. Now, envelope connection. Traffic from TCP or IP layers is encapsulated in Ethernet frames, then tagged with VLAN info, turning them into envelope frames before being transmitted. So that's how it is connected in TCP/IP. So there's connection to IP address. Then on the switch, the other end, interface range, gig 1/0/1 to 2, meaning it selects two switch ports, gig 1/0/1 and gig 1/0/2. So for example, you have a switch on the other hand. To be able to connect the two switch supported trunking, you need to put this in Linux. So select the two switch ports, gig 1/0/1 and gig 1/0/2, that connects to your two servers, two INCs, ETH0 and ETH1. So those are the line that connect your two server from one switch to another, or from one station to another. Channel group 1, mode on, so it groups these ports into one static ether channel. Manual banding. No LACP negotiation. This matches your Linux banding configuration. So when we use mode, basically, since we are already imported it, this group or groups, it will group these ports into one static ether channel, or you will use manual banding, no LACP negotiation. This matches your Linux banding configuration. So after we created that interface range connecting different trunk ports, we are now banding it. So why both sides must match? So if Linux uses a manual banding and the switch expects LACP, which is the automatic one, the switch won't treat both links as one logical channel. Packets get out of order and will drop. So this line 3, switch port mode trunk, so mix these port trunk ports, meaning they carry traffic from multiple VLANs, so each tagged by 802.1q headers. So this is how we activate the trunk and how we need to use now the header or tag header. So envelope connection, all traffic across this trunk line is carried as VLAN tag envelope frames, each containing VLAN ID. So all traffic across this trunk line now will now have the envelope or VLAN ID and possibly cause priority bits. This line 4 switch port trunk allowed VLAN 10, 20, meaning it specifies which VLAN this trunk will carry. In the case VLAN 10 and VLAN 20. So basically, we're gonna define what VLAN will be included in this trunk. In this case, we have VLAN 10 and VLAN 20. So those VLAN 10 and VLAN 20 could have, again, multiple NICs or hosts. The switch only forwards frames with these VLAN tags on this trunk. Envelope connection, this VLAN ID corresponds to the tags that Linux added with vconfig add band 10 and 20. Thus, both sides interpret the same envelope tags. Switch 4, line 5, switch port trunk native VLAN 10, meaning it declares VLAN 10 as the native VLAN. So, meaning untagged frames on the trunk will be treated as belong to VLAN 10. So, it still belongs to the trunk, but all of untagged frame will be sent to this VLAN. So, envelope connection, if Linux sends an untagged Ethernet frames without a VLAN tag, the switch will wrap it logically into VLAN 10. This is how envelope frames may have tags and others may not, but both are understood consistently. So the big picture connection to TCP or IP diagram: physical cables or NICs, layer 1, data link, Ethernet or VLAN. So in this Ethernet, you can have VLAN because you separate that into different LAN logically. So it has the bonding VLAN 802.01p/q tags. So this is how you do the switch as well, the trunks. Network IP layer 3, transport TCP or UDP layer 4, application HTTP or SSH. Here's what happens end to end. TCP or IP layers generate packets HTTP to TCP to IP. Ethernet layer on the band 0.10 wraps the IP packet into an Ethernet envelope frame. It adds VLAN tag 802.1q and possibly priority 802.1p. The bonding driver decides which physical NIC sends the frame, ETH0 or ETH1. So because you have a band, that bonding driver, if it's automatically configured, will decide who is available, which ETH0 or ETH1 frame or Ethernet. The switch receive the tag frame on a trunk port. So now it will be received by the switch on its trunk port. It will see the VLAN ID and forwards it within VLAN 10 or 20 depending on the destination address. So the receiver unwraps the envelope, passes the IP payload up to layer 3, 4 until 7. So summary of the relationship: bonding layer 2, purpose combine multiple links. It is connected to physical layer and Ethernet. VLAN 802.1q layer 2, purpose identify logical networks, connects to envelope frames. QoS 802.1p layer 2, purpose prioritize traffic, connects to envelope frame priority bits. It is connected to envelope frame priority bits concept. Envelope frame layer 2, purpose extended Ethernet frame tags plus payload, connects to TCP or IP payload container. So this is how you put the IP payload. TCP or IP layer 3 to 7. So there's the TCP and IP. As you can see, most of it, all of them is layer 2. The TCP or IP is only the layer 3 to 7. And the purpose, logical data exchange, and then connects to inside envelope frame. So this is what we see inside the envelope frame. Now step 1, the real world situation. So let's visualize like Wi-Fi. Laptop A connected to wireless Wi-Fi and then to router, and then laptop B connected to internet. Laptop A Wi-Fi connects to your router's wireless interface. Laptop B Ethernet connect to one of the router's wired LAN ports. Router connects to Converge Fiber Network, your 1299 plan. Even if both laptops can see each other and access the internet internally, each interface, Wi-Fi and internet, is a separate layer 2 network. So your router decides whether they're bridge, same LAN or subnet, or segmented, different VLANs or subnet. So different VLANs if it's connected to the Converge access switch, that's a different VLAN. But for the home host, that's in VLAN 10. So step 2, where VLAN fit and why they separate IP traffic. So let's recall TCP or IP plus OSI layering. Layer 1 physical, what it does: wires, radio waves, fiber. Example, Wi-Fi, radio, Ethernet cable. Layer 2 data link, what it does: local delivery between devices, frames. Example, Ethernet, Wi-Fi, VLAN. So even Wi-Fi is in the layer 2. Network, logical addressing and routing packets. Example, IP, ICMP. Layer 4 to 7, transport to application. What it does: end-to-end data flow. Example, TCP, UDP, HTTP, etc. Now, VLANs, IEEE O2.1Q live at layer 2 data link. So they're in the Wi-Fi. They don't change your IP packet. They tag the Ethernet frame that carries that packet. So that's amazing about this is that this is abstracted from your IP or TCP to IP layer. So that packet is just being wrapped, whether it's Wi-Fi signal or direct connection to port. Now step 3, VLANs as envelopes that separate traffic. Without VLANs, your Ethernet switch or router's internal switch treats every connected port as part of one big LAN. So your router switch actually separate your host VLAN is what separates your host VLAN to the one connected to Converge. So like this, so everyone is on the same broadcast domain layer 2. Everyone shares the same IP subnet 192.168.1.0/24. A broadcast ARP packet from one host reaches all others. Now if you enable VLANs, now we have this switch or router and router LAN. VLAN 10, we have Wi-Fi ports, SSA ID home for that, and then another is tough PCs for Ethernet. Now VLAN 20, that's where your guest Wi-Fi or SSID guest. VLAN 10 traffic stays within VLAN 10. VLAN 20 traffic stays within VLAN 20. They can see or ARP each other. They're isolated at layer 2. Each VLAN is like a separate virtual switch carrying its own set of Ethernet envelope frames. So they have a different frame format because they have different VLAN. Step 4, the envelope analogy with your setup. So let's visualize what happens when your Wi-Fi laptop VLAN 10 pings your Ethernet laptop VLAN 20 on a separate VLAN. Without VLAN, which is the same subnet, Wi-Fi laptop creates an IP packet, source 192.168.1.10, destination 192.168.1.10. The IP packet is placed inside an Ethernet frame layer 2 envelope. Router switch deliver it directly to Ethernet laptop. No VLAN tag, one shared network. So with VLAN separated subnets, what happened is first Wi-Fi interface SSID equals to VLAN 10 sends the same IP packet. So these are the Wi-Fi and you connect the Wi-Fi interface, which is the SSID, right? You need to know the password. Is equals to VLAN 10. You send the same IP packet, but now the Ethernet frame gets tagged. You have dest MAC, SRC MAC, VLAN tag equals to 10, type IPv4 IP payload. The router sees the VLAN 10 tag. It keeps it isolated from VLAN 20. To reach laptop beyond VLAN 20, it must go to layer 3 IP routing inside the router. The router removes the VLAN 10 envelope. It reads the IP header, routes it to VLAN 20, encapsulate it in a new Ethernet frame, tag VLAN 20. So the router will actually routes it to VLAN 20 and re-encapsulate that into an Ethernet envelope. Ethernet frame tag VLAN 20 to be able to send it to VLAN 20 because you need a header in the Ethernet frame, and then the VLAN 20 will now decapsulate it on its end. So in short, VLAN separation at layer 2 forces traffic to go through layer 3, the IP router, to cross VLANs. So again, in short, VLAN separation at layer 2 forces traffic to go through layer 3. The IP router to cross the VLANs. So if you have one shared VLAN, you don't need to actually cross that IP or decapsulate it using a different envelope frame format. That's why VLAN correspond to different subnet. So that's what we mean with VLAN being a different subnet. So think of each VLAN as a logical neighborhood under the same physical city, your home network. So layer 1, object in your home, the cables or Wi-Fi airwaves. Layer 2, streets with address sign, Ethernet frames, VLAN tags. Layer 3 IP, the actual house address, IP address. Layer 4 and 7, the people talking, applications, ports. So when you separate VLANs, you're seeing these groups, streets are fenced off, cars, frames can drive across. Only carriers, routers at layer 3 can carry messages between them. So that's what you mean when separating it by VLANs. Because they are fenced up and they have different they could have different Ethernet frame format. That's why each VLAN usually gets its own IP subnet. Like VLAN 10, we have a subnet 192.168.10.0/24. Devices, home, Wi-Fi, laptops. For VLAN 20, we have a subnet 192.168.20.0/24. Devices is work Ethernet laptops. Now the router layer 3 has interfaces on both. So band.010 is binded to 192.168.10.1 and band.20 is binded to 192.168.20.1. It knows how to route packets between them if allowed. So step 6 in your converge setup, your converge ONU /router already use VLANs internally. One VLAN carries your internet service uplink to ISP. Another VLAN carries your LAN traffic, Wi-Fi, and Ethernet. So that VLAN is what separates your Wi-Fi connection and Ethernet from your laptop, and the VLAN to converge access link. If you configure your Wi-Fi, your guest Wi-Fi, it's usually another VLAN with its own IP subnet. So if you now configure your router to be able to have a guest, Wi-Fi, you're actually creating another subnet. So your laptop via Wi-Fi and laptop via internet could be in the same VLAN or subnet 192.168.1.x. It can ping each other's directly, or in different VLANs or subnet 192.168.1.x versus 192.168.2.x. It must go through router's IP layer first. So summary concept: VLAN 802.1q layer 2. Function: it tag or segregate Ethernet frames. Example in your setup: Wi-Fi guest VLAN 20 versus VLAN 10. IP subnet layer 3, assign logical address groups. Example in your setup: 192.68.10.0/24 versus 192.168.20.0/24. Router layer 3, move packets between subnets / VLANs. So that's what move packets between different VLANs. Example in your setup: converts ONU doing NAT. So that's the converged router doing the NAT or address translation. Banding layer 2, combine multiple links like ATH0 to ATH1. Server trunk to switch. That's the example in setup. Server trunk to switch. Envelope frame layer 2. Function: Ethernet frame with VLAN or COS tag. Example in your setup: what actually carries the IP packet. So yeah.